My name is Joseph Azevedo, and this is my lab report for Lab 2. In this report, I'm going to go over the purpose of the lab, the fundamental physics principles involved, the procedure involved, and measurements taken, the computational model created to aid analysis, and finally, the results of the lab, during which I revised the charge of the 18 centimeter long charge tape based on measurements from Lab 1 to be around positive 19.9 nanocoulombs. So, starting off, the purpose of this lab was to explore the ways in which charged objects interact, and to use those observations to estimate the excess charge on charged pieces of clear tape. Specifically, it was to refine the observations and analysis performed in Lab 1 to develop a better model and produce more accurate results. To do this, we're going to rely on a handful of fundamental physics principles, many of which are the same as Lab 1. On top of these, we're going to add the distribution of electric charge for non-point objects, which will help us create a better model for the charged tapes. To review the procedure of the previous lab, which this lab is an extension to, I first determined the charge of specially prepared pieces of clear tape to be positive via an object, namely a clear plastic pen, with a known charge. Then I set up two pieces of tape, A and B, and suspended tape B across a distance. Afterwards, I slowly moved tape A underneath tape B until I observed tape B beginning to float. This is due to both pieces of U-tape having a positive charge, and since like charges repel, the electric force by tape A on tape B causes tape B to float. During this, I also noted the length of the floating piece of tape B and the distance at which they began to float. Now that we've finished recapping the procedure, we can move on to the updated analysis, where I improved upon the computational model from Lab 1. To do this, I first refined a simplified model of the problem, which involves a few key assumptions. First, that the charge of each piece of U-tape is identical and evenly distributed across its surface. Second, that because the charge is evenly distributed, we can instead model each piece of tape as a line charge running down the length of it with a constant linear charge density. Third, we consider only the section of the tape that is floating and ignore any other forces, such as air resistance or tension. Given these assumptions, we can finally construct a model where tape B exists as a line charge that is positioned above tape A. Because tape B is stationary within our frame of reference, we know that the net force acting upon it must be zero, by Newton's first law of motion, and it is in equilibrium. By first calculating the mass of the tape via its length and linear mass density, we can use Newton's second law of motion and the acceleration due to gravity on the Earth's surface to determine the magnitude of the force that tape B experiences due to gravity. Because the net force is zero, we know that the magnitude of the force on tape B created by the electric field for tape A must be equal to the magnitude of the gravitational force. However, determining the interaction of two line charges analytically would involve a complicated derivation, so I instead opted for a solution using many discrete point charges with the aid of a computer model. In this, we model each line charge as a finite collection of small point charges evenly distributed across its length. This allowed me to estimate the charge needed for the forces to balance each other out, and was the primary functionality of the GlowScript code I modified from the lab starter code. I'll take a second to walk through the major parts. First, it defines the physical constants, observed values, and helper functions. Then, it includes the code to visually display the experimental setup. The most important part of the script is the actual implementation of the model, where it iterates through each combination of small point charges on the top and bottom tape and determines the electric force enacted upon the small point charge on the top tape. Then, by summing the small forces up from each pairwise combination, it obtains an estimation for the total force on the top tape. Finally, it includes some code to print out the results and create the force arrows. So, given this model, I was able to obtain the following results. The charge on each piece of tape using the idealized model was determined to be around positive 19.9 nanocoulombs, using 30 discrete point charges per line charge. This represents a 123.6% increase compared to the estimate obtained in Lab 1, where I chose to instead model the charges on both pieces of tape as identical point charges located at their centers and estimated the charge on each to be around 8.9 nanocoulombs. These estimates likely differ simply because they model the charge with different distributions, and that affects how it falls off and affects other objects around it. Compared to the estimate in Lab 1, the estimate obtained from this lab using the updated model is likely closer to the actual value, as the model is more accurate since charge isn't distributed in a single point in reality. With that in mind, this model isn't perfect either, as we also know that charges in insulators aren't uniformly distributed. And, of course, pieces of tape aren't lines with infinitesimally small thicknesses. In conclusion, in this lab, we further explored the ways in which charged objects interact, and we used a new computational model to further refine the results obtained in the previous lab to ultimately estimate the excess charge on short pieces of clear U-tape to be around positive 19.9 nanocoulombs.